Hi, we're continuing our series in the Reynolds transport theorem. Today we're going to look at the energy equation. So there's the energy equation, and let's go over each term. So the first term is the pressure difference term, or the pressure head. The second term is this kinetic energy. Third is the potential energy. This first term on the right-hand side, H of F, is the total friction, which includes the major and the minor losses. And then we have the turbine, which has the same sign as the friction. They're both positive. They're both pulling energy out of the flow. And then finally, you've got the pump head, which is negative. And each one of these terms has units of length, which is why it's called a head. So head pressure comes from the idea that if you had a pump and you connected it to a pipe that just went straight up in the air, and you ran the pump, pumped water up till you could pump it up so high and it stopped, that height that it would achieve is called the head. So you can convert any of these pressure drop, kinematic viscosity, potential head to a head. To get to this equation, we had to assume steady and compressible plug flow with no heat transfer. Sometimes you'll see the energy equation written with like a correction term, like alpha or beta, like we did for the momentum equation. That's really there just to kind of fix up this plug flow assumption a bit and include some variation for the boundary layer, but it's just a Band-Aid, really. Now, oftentimes it's a great source of confusion that this looks so much like the Bernoulli equation. People say it is the Bernoulli equation. Well, it's not. There's two big differences. One, it was derived from momentum and applied to a streamline as opposed to a control volume. So we're going to apply this guy to a control volume. So, I mean, maybe I'm splitting hairs here, but it's important, I think, to recognize the differences. All right, so in the previous lecture where we talked about momentum, we derived this expression for the dimensionless shear stress over the dynamic pressure, which is this 4 shear stress at the wall divided by the dynamic pressure, first formulated by Henry Darcy. So Mr. Darcy got that factor named after him. And we derived this set of relationships that relates the friction to the pressure loss and then to this expression, the dimensionless expression for non-dimensional shear stress. How do we get this Darcy friction factor? Well, you recall we're going to get it from the Moody diagram. So we have the energy equation, we have our friction relations, and this representing the major losses goes right into our energy equation here. To get the Darcy friction factor, recall it's a function of Reynolds number on the x-axis, which is either can be expressed in terms of the dynamic or shear viscosity or the kinematic viscosity, and the roughness. So the roughness is listed here for various construction materials, this being literally the size of the bump for a commercial asphalt pipe or whatnot. So the roughness factors are written over here. So you would basically find your Reynolds number, read up till you hit the line for your roughness factor, and then read over what your Darcy friction factor is. Recall that this is the turbulent region here. All of this is for turbulent flow. And as the Reynolds number gets below the magic number of 2200, the flow becomes laminar, and then you're on this line here with some small region called the transition zone. Hopefully you'll never end up there. But the Reynolds number for laminar flow, or the Darcy friction factor for laminar flow, is just a 64 of a Reynolds number. All right, let's do a quick example. The pressure drop in 200 feet of 6-inch diameter asphalt cast iron pipe carrying 6 feet per second. So this is the average velocity of the water. Which one of those is the pressure drop? Well, we can solve this by using the energy equation. Here's our pressure drop here. This is what we're after. We recognize that if it's a constant diameter pipe and it's already at, and it's not compressible, then the average flow in every section, the average mass flow rate must be the same, and therefore the area being constant, the density being constant, the velocity must be constant. If it's horizontal, there's no change in elevation. There's no turbine or pump in this control volume, so we end up with this relationship that we've talked about before, that the pressure drop and the frictional head loss are equivalent. So basically, you can think of this as this is what's making the flow go, the pressure difference, and that energy that we put in as pressure difference is being sucked up by the friction. All right, so we need that F-Darcy friction factor. So we're going to need the Reynolds number and the roughness. So calculate the Reynolds number, 6 feet per second times the diameter. I look up the density and the kinematic viscosity of water, and I plug that in, and I get a Reynolds number of 2.8 times 10 to the 5th. That's a reasonable Reynolds number. You're looking for something in the 4th to the 5th to the 6th for Reynolds number. The relative roughness, we got this cast iron pipe here, so I can again look there on the Moody diagram between 0.0002 and 0.0006. So I'll take the average and I get this 0.0008 is the dimensionless roughness over the diameter. So together, I should be able to get the friction factor. So I'm going to go to the Moody diagram. I'm going to look up my Reynolds number, so it's somewhere along that dotted line, and then I find the roughness for this particular pipe, and I go to the intersection of this pipe roughness there, and then I read across to there. So I find the intersection of the roughness and the Reynolds number, and I read it across. I get a friction factor of 0.02, sorry. Yeah, 0.02. So now it's pretty easy to solve for this. I've got my expression. I can solve for the total friction loss. So in terms of feet of head, my friction loss is 4.5 feet a head. So that means it's pulling that much head off of the flow. And I can use that head then to solve for the pressure drop. And I get 1.9 psi. So again, is this a relative or an absolute pressure? It doesn't really matter because it's a pressure difference. So it's 1.9 psi or psi-g or psi-v. All right, hope you enjoyed it. Hope you learned something. Try some problems.